So in this histogram are the final grades for my algebra classes, and we're going to take this and turn it into a relative frequency table. Remember, a relative frequency table is based off a percentage, not just a counts. So first we should take a look at the counts in our histogram. Alright, and now we're going to make our table. So we're going to set up with our grades. These are going to be our intervals, and we have our frequency, and we have our relative frequency. So our first bin in the histogram is 50 to 55. Remember, not including 55. Almost there. And our last interval to 100. Alright, so we saw in the first interval there was 1 data point, 2, 5, 6, 11, 10, 7, 4, 3, 1. Alright, so we know the relative frequency is changing into its percentage. There are 90 data points, or 50 data points altogether. So one of them out of 50, that is 2%. 2 out of 50, 4%, 5 out of 50, 10%, 12%, 22%, 20%, 14%, 8%, 6%, and 2%. And hopefully this all adds up to 100. 2 plus 4 is 6. We got 16, 28, 28 plus 22 is 50, 70, 84, 92, 100%. So that's good. So the next thing we're going to do is we're going to redraw the histogram to show its percentages instead of the counts. So our new histogram is going to look something like this. We're going to have the same exact intervals. And we'll make sure we include our labels. Except this time we're going to plot the percentage instead of the count. So instead of writing the percentage, I left them as their decimal, as the proportion. So we saw that in the first bin, we had 2% of the data in this interval. The next one was 4%, 10%, 12%, 22%, 20%, 14, 8, 6, and 2. So besides my poor drawing, we can see that the shape of this doesn't change. So my first question is we want to find the center of student scores. What's nice about using the relative frequency instead of the counts is that we know what these percentages are. So we know this is 2%, 4%, we know this is 10%, 12%. Therefore, it's going to be easy to find the center. The center is going to be the 50%. So 50%, that's 6, 16, 28, it's 22%. So it's going to fall within here, 70 and 75. Since we don't know exactly what the data is, we can only write down that the interval is between 70 and 75. What proportion of students that score between 50 and 100? Well, here's 50, here's 100. That would be 100% of students are within that interval. So if I collected data from more and more students, eventually we'd be able to draw a curve to describe this overall pattern. This smooth curve is called a density curve. So looking at our data here, if I asked more and more students, eventually I'd be able to draw a nice smooth curve that would fall over top of our histogram. And that curve itself is called the density curve. So here's another example. You can notice that at first, with only 5 intervals, or 5 bins, the shape is kind of strange. I mean, it's obviously symmetric, but the more and more trials you take, the closer and closer it gets to this perfect density curve. So the density curve has several characteristics. The first one is that it is on or above the horizontal axis. It will never intersect the axis or go below. The other characteristic is that the area underneath this curve is going to add up to 100%. The last characteristic is that this describes the overall pattern. So it describes the overall pattern. So this right here is a normal density curve. It describes the overall pattern of the histogram. The area under the curve are proportions, so we don't use counts, we use the relative frequency, and outliers are not typically described by the curve. So no set of data is exactly described by a density curve. The curve is an approximation. It's easy to use and it's accurate enough for our practical use. So we want to verify that the following is a density curve. Our first characteristic is that it does not cross the horizontal axis, so it doesn't. It just is right here. It's right on it. And next we want to legitimize it by making sure that the area underneath is 1. So we have a triangle, basically, and we know that the area of a triangle is 1/2 base times height. In this case, our base is from here to here, 0 to 2, so our base is 2. Our height is from here to here, which is 1. And 1/2 times 2 times 1 is 1, so we have a legitimate density curve. Next we want to find the proportion of the data that is between 1 and 2. So this is telling us that we're looking for the probability or the area. They both mean the same thing. So between 1 and 2, here's 1, here's 2. So essentially we're looking for this area right here, another triangle. So same process, 1/2 base times height. This time our base is from 1 to 2, which is only 1. Our height is from here to here, which is approximately 0.5. So the area between 1 and 2 is going to be 0.25. Same idea with the next question. We're looking for the probability of a value being less than or equal to 1. Another way of reading this is we're looking for the area that is less than or equal to 1. So here's 1. One way we could find this is we could break this up into 2 pieces. We could make I guess it would be a rectangle. So we could find this rectangle and this triangle separately. Let's practice that. So we have a rectangle and a triangle. In our triangle, our base this time is from 0 to 1. Our height goes from 0.5 to 1, so that distance is 0.5. And for our rectangle, our base is from 0 to 1, and our height is from 0 to 0.5. We put this all together, we get half of 0.5, which is 0.25, plus 0.5. This area would be 7.75. Another way we could do it is that since we already found this area over here, we know that this entire area equals 1. We could do 1 minus 1/2 of the triangle from 1 to 2. We knew that that was 0.25, and we get the same answer. So 2 different ways to find the area of the proportion of observations that are between those two values. Letter C, we're looking for the probability of a value being 1.5. So here's our 1.5. This is actually not possible. The reason it's not possible is because we're talking about area. It is impossible to find area that is below a certain point. So in calculus, we learned it's not possible to find the area under a single point. Therefore, in statistics, we use the symbols less than and greater than interchangeably with less than or equal to. So for example, if I wanted to find less than or equal to x less than or equal to 2, it would be the same thing as finding 1 less than x less than 2. So both notations are correct. They mean the same thing. So having said that, I'd like you to pause the video and see if you can determine whether or not the following is a density curve. And if you can, I'd like you to find the area of each of these observations. Since density curves can come in any imaginable shape, but there are some that are more common than others. So just like we know from distributions from Unit 1, we know that this is going to be a skewed density curve, specifically skewed to the right because the tail is on the right. We know that this one right here is a uniform density curve. If you had many observations over and over and over again that look something like this, we would say it's uniform. This one is highly unusual. We don't typically see this one, so this is a weird one that we don't really know. And finally, we have the most infamous. This is a normal density curve. Much like we saw in Unit 1, the mean and median's location in a distribution is very similar to the distribution in a density curve. So here in our normal density curve, we saw that before, and when it was symmetric, the mean and median were in the same spot. Same thing here. In a normal density curve, the mean and median are right down the center. For skewed right and skewed left, the same thing applies that we learned from distribution The mean is the one that's most affected by the outliers, therefore it is closest to the tail. The median, not so much. So I am just approximating where the median and the mean would be. So when we're talking about density curves, the mean is described as the balance point. So if you imagine that the density curve was a solid object, the mean would be where the weight would balance. The median, on the other hand, is the halfway point. It's exactly in the center, so it's the point at which the areas on both sides of the median are equal. So take a moment, pause the video, and see if you can determine which of the following figures have a mean at A, B, or C. So checking our work, we know that this is a skewed data set. We know that the mean is the balance point and the median is where it cuts the data in half. We also know that the mean is going to be closest to the tail. So in this case, it probably makes more sense that the median is B because A doesn't look like it cuts the area in half at all. So the median is probably B, and C is closer to the tail, so that must be our mean. Here we know that since this is symmetric, the mean and the median are going to be down the center in the same spot. And in figure C, again, if we're looking for the median, we know it's going to cut the area in half. Probably not going to be C. It's more likely the median is B, and therefore, since the mean gets pulled towards the tail, the mean must be A. So, when we take actual observations, we call that a sample. The mean we've been using is x bar, and the standard deviation symbol we've been using is SX. So, since we're comparing this to an idealized description of the distribution, the mean we call something different. We call it mu, and the standard deviation we call sigma. So again, to make the distinction, we have to show that when we're looking at actual observations, these are the symbols we use for mean and standard deviation. When we're talking about a density curve, remember it's hypothetical, it's theoretical, idealized description. Our mean is mu, our standard deviation is called sigma. So in a sample, our symbols look like this. In a density curve, our symbol looks like this. And I put this little cow here to remind you that this symbol sounds like mu. Sounds like a cow. So one important class of density curves are called the normal curves. And yeah, it's weird, but anytime you're talking about a normal curve, it's going to be capitalized. And a normal curve describes a normal distribution, which we know is symmetric. Look, I already made the mistake, capital. So we know that it's symmetric, but it also follows a special shape. It follows a bell curve. A normal curve is sketched using the mean and standard deviation of the distribution. We know that in a symmetric data set, we use the mean and standard deviation to describe the center and the spread. And the way we denote this is a capital N, mu, and sigma. So here's an example of a normal curve. So right down the center we know is going to be mu, or the mean. The rest of the normal curve is used by filling in the standard deviation. If you take one step to the right, we call that one standard deviation. If we take another step to the right, we call that two standard deviations. And then one more step, we call that three standard deviations. Yes, it does go beyond 3 standard deviations. However, typically when we do a normal curve, we stop at 3. Now, if we start back at the mean and we go to the left, we are going down. So this is -1 standard deviations. one more step this way takes us to -2 standard deviations, and one more step takes us to -3 standard deviations. Yes, it is possible for the curve to continue going to the left. Typically, we stop from -3 to +3 standard deviations. So what we mean by this is going to make more sense in a second. So in example 1, we have normal distribution with n 16 and 4. So we know from this that this is going to be normal. We know from this, in our notation, that the first number is going to be our average, and the second number is going to be our standard deviation, or our sigma. So I'm going to sketch the density curve. It looks like this. And I'm going to make a mark for our mean, and I'm going to make 3 marks for our standard deviations on the left and our standard deviations on the right. So we know right down the middle is our mean, which we know is 16. If you are 1 standard deviation away from the mean, that means that you are a distance of 4 away. So 1 standard deviation means that you are now standing at 20. 1 more standard deviation means that you're now standing at 24. 3 standard deviations is 28. Yes, we could go further, but again, we're stopping at 3 standard deviations. If we're going to the left, we're not going to add, we're going to subtract. So that takes us to 12. We have 8, then 4. So for this data set, we don't know exactly what the data is. We could have values that are beyond 28. We could have values that are beyond 4. But the majority of our values are going to be between 4 and 28. If you're 1 standard deviation away from the average, you could get a score of 20, or you could have a score of 12. If you're 2 standard deviations from the mean, you could have 24, you could have 8. Let's do one more. So same idea, we're sketching a normal curve. This n tells us it's normal. This tells us our mu, this one tells us our sigma. So we're going to sketch our normal distribution. So right down the center, we know is going to be our mu, which is -5. Our standard deviation is 2. We know that it won't be anything smaller than 2. Standard deviation, since it's always going to get squared, is always going to be larger than or equal to 0. So 1 standard deviation away from the average is going to be -5 minus, or plus 2, so that's -3. Plus 2 is -1. And we take one more step away, we would be a +1. If we go below the average, we would get -7, -9, -11. So in this particular case, the majority of our data would fall between -11 and 1. It is possible to have data that is greater than 1. It is also possible to have data that is less than -11, but it is highly unlikely. So let's put it in context. The battery life of Duracell batteries are normally distributed, with a mean battery life of 42.3 and a standard deviation of 8.2. We're going to sketch this curve. So we know right down the middle is our mu, so the average battery life for this batteries are 42.3. Then we're going to add our standard deviations because they're above the average. Here, our standard deviations are below average. So if we were looking at all of the data of Duracell batteries, you can see that the majority of batteries last between 17.7 and 66.9 hours. Yes, there are outliers that go beyond these points, but the majority fall in this range right here. So if you're a battery that lasts 50.5 hours, you are 1 standard deviation above the average. If you have a battery that lasts 34.1, you are 1 standard deviation below average. So any of the values that are below average are obviously going to be smaller values than the ones that are above the average. It's really important to note that when you're sketching a normal curve on the AP test, you have to include your labels. So you have to include these numbers on the bottom for scales. So the last thing that we want to look at is what happens to a normal curve when you change the mean and you change the standard deviation. So know that the mean is the center. If you change the center, that means the whole standard deviation is going to keep its shape, but it's going to move left and right. So if you increase standard deviation, that means that the shape stays the same, and I'm trying to sketch this roughly the same. So this is what happens when you increase the average. Everything shifts to the right. If you're decreasing the average, that means that we take the whole shape, it stays the same, but the center is going to shift to the left. What happens if you change the standard deviation? Well, standard deviation tells us how spread apart the data is. So if you want to change the standard deviation to something larger, you know that it's going to be less consistent or more spread out. So it would look something like this. The center stays the same. We're not changing the mean. We're just showing that the standard deviation is larger, which means that it's much more spread out. Consequently, if you have something that's a smaller standard deviation, it's going to get much skinnier. This is what happens when you decrease. That means that the data is really close together. So notice, if you change the mean, the shape stays the same. But the curve moves up or down. If you change the standard deviation, the center stays the same, but the shape gets fatter or taller. If you change both, then you can imagine both the center changes and the shape changes. So for example, if we increased our mean and also increased our standard deviation, we would get something like this. This would be an increased mean and an increased standard deviation. Because the standard deviation is getting wider, that means the data is spread apart, and since our average is also getting larger, the center is going to shift upward on positive numbers.